I'm Kush Bhatia, and I will be presenting our work on agnostic learning with unknown utilities. This is joint work with Peter Bartlett, Anca Dragan, and Jacob Steinhardt. In classical decision problems, one often begins with a dataset consisting of n data points. These consist of feature or context vectors xi and corresponding labels or decisions yi. The central objective in most scenarios is to learn a classifier to predict the labels y correctly given context vectors x. Within this paradigm, most works, if not all, implicitly assume that all mistakes are equally costly and that each scenario X is equally important. In reality, though, this is often not the case. For instance, consider the classification system designed for a self driving car. The cost of mispredicting a roadside post of box versus that of missing out on a stop sign can actually be very different. Furthermore, consider the two scenarios shown in the picture. One where a person is crossing the road, and the other where the person is walking far away from the roadside. Clearly, identifying the person correctly is far more important in the first case as compared to the second one. In our work, we posit that each decision taken by the learner has a context dependent utility or a negative cost. Furthermore, key characteristics of this utility function are that A, it is unknown to the learner a priori before the task begins, and B, that it is necessary for the human to communicate it to the learner in some form. Given this unknown utility, the question here is how do we communicate this function to the learner? The first option is to possibly get a human expert to write down this complex utility function mathematically and hand it over to the learner. However, this option can be prone to serious errors since it is very hard for an expert to imagine all possible scenarios a priori and encode them in the utility function. Another option is to allow the agent to learn this utility function from observed decisions. Such a paradigm has been studied in the economics literature as learning from revealed preferences and in the machine learning community as inverse reinforcement learning. The main idea here is to allow the learner to infer the underlying utility function by exhibiting optimal decision making in different scenarios. However, most of the techniques studied here assume that this utility function lies in some well-specified class of functions, say linear in some feature space, and it offers no guarantees on their performance in the face of slight misspecification. Hence, both these options are not actually suitable to communicate this unknown utility function. In order to overcome the limitations of these existing options, we introduce our framework of agnostic learning with unknown utilities, wherein we place no assumptions on the underlying utility function U star. Formally, the learner is presented with a dataset of n points, each of which is sample IID from some unknown distribution D. We denote by script f the decision function class, wherein each function f is a mapping from the context space x to decision space y. Further, we denote by u star the true utility function, which is again unknown to the learner. This utility function maps contexts and corresponding decisions to rewards in a bounded interval. Lastly, there is an information oracle with which the learner can interact and get more information about the different decisions y and the underlying utility u star. As I mentioned earlier, our framework moves away from placing any assumption on the underlying utility function u star and instead posits that the decision-making function can only be selected from this restricted class f. Given this framework, the objective of the learner is to output a function f hat such that it has small excess risk when evaluated on this unknown utility function u star. Observe that this is just an evaluation criteria and that the true utility is never revealed to the learner. With this setup, the key question here is what should be this information oracle? We would ideally like this oracle to be powerful enough to make learning feasible, but it should not be overly complicated for human experts to answer the queries. Before we discuss this issue in detail, I wanted to mention that going forward, we will restrict our attention to the binary classification problem where the label space y consists of two labels, a blue label and a green label. Coming back to the information oracles, the first contender for such an oracle is the value oracle. In this oracle, given a context X and a decision, the human expert provides the exact value of the underlying utility function. However, note that the underlying utility function can be quite complex, and this actually makes it very hard for human experts to accurately provide these value judgments. This actually makes it infeasible to deploy such an oracle in practice. On the other hand, it is often easier for humans to provide comparative evaluation based on these utilities. For instance, one can query the human with a context and a pair of decisions, and it can respond by indicating which of these two has a higher utility. We call this the comparison oracle. Such comparative feedback, however, is severely limited in the information it provides to the learner. For instance, consider the problem where we have three clusters of data points, x1, x2, and x3. The color of the data point here indicates which of the two decisions has a higher utility. For instance, for the cluster x1, the green decision has a higher utility than the blue one. The shaded areas mark the predicted decisions for the two classifiers f1 and f2. Observe that both classifiers f1 and f2 make the same number of mistakes. F1 mispredicts x3 while f2 mispredicts x1. Also, just by interacting with the comparison oracle, no learner will be able to understand the relative costs of these mistakes. Indeed, no learner can understand the precise trade-offs between the different mistakes, and one can actually show a strong statement which says that any algorithm will suffer an excess risk which will be order 1. Thus, this comparison oracle, while being easy to implement on the human side, is actually information theoretically limited. We can go to the other extreme, and one can imagine an extremely powerful oracle, which we call the infinite comparison oracle. This oracle takes in two functions, f1 and f2, and outputs which one of those has a higher utility when evaluated on the true distribution D. Note that this oracle can actually be used by a learning algorithm to figure out the best decision function in the class F. However, it places all the burden of learning on the human expert, asking them to effectively compare decisions across an infinite number of contexts. Thus, while being information theoretically optimal, this oracle is practically infeasible to implement. To overcome these limitations of existing elicitation mechanisms, our work proposes a new type of comparison oracle, which we call the K-comparison oracle. This type of information feedback interpolates between the vanilla and the infinite comparison. It gives the human expert a bucket of k different contexts, x1 to xk, and two sets of associated decision vectors. The human is then required to compare these two bundles and output which of these two has a higher combined utility. Note that one can recover the vanilla and the infinite comparison oracles by setting k equals to 1 and k equals to infinity respectively. It's also important to note here that as the order k of the comparison oracle increases, it gets harder and harder for the human to provide this feedback. Going forward, we'll focus on our problem of agnostic learning with unknown utilities, where the information oracle is the k comparison oracle. We will describe our main algorithm which interacts with the k comparison oracle to output a function f hat, and we'll also study its statistical properties. Let's begin with our main algorithm. In this figure, the x-axis represents the different data points. The color of each data point again represents the decision with the higher utility. The y-axis represents the utility gain, that is, how much additional utility can a classifier gain by predicting green versus blue for any particular data point. Further, for illustration purposes, we'll restrict f to be the class of threshold functions, and each function f will therefore partition the space into a blue and a green region. Let's begin with a slightly easier problem where the underlying utility function u star is actually known to the learner. In this case, the learner can simply output the function f, which maximizes the utility on n data points, and this is also called the empirical utility maximizer. This function, FERM, is known to have good generalization properties depending on the class of functions f. However, since in our problem the utility function u star is unknown, the learner cannot output the ERM function. Instead, our algorithm consists of a two-step plug-in estimator. In the first step, this estimator obtains estimates u hat of the utility on the sample data points by interacting with the k-comparison oracles. The vertical bars on the data points reflect this estimation error. In the next step, the learner simply outputs the empirical maximizer with respect to these estimated utilities. In the plot, this is shown by the threshold function f hat alg. Given this procedure, I will now explain in detail how the first step, that of estimating the utilities, works. To, to obtain estimates u hat on the sample data points, the algorithm begins by finding the data point x max, which has the maximum utility gain. This data point is highlighted in the figure on the right. Notice that this can actually be obtained by simply using two comparison queries. For instance, to compare the gains of the data points x1 and x2, we can ask a query comparing both blue decisions for x1 and x2 with both green decisions. This query effectively provides a comparison between the utility gains of x1 and x2. Once we have the ability to compare two data points, we can find the one which has the maximum utility gain. Once we have the point x max with us, the algorithm can use this to estimate the utility gains of each data point using k comparisons. In order to see how, consider the point x prime in the figure on the right. For some value of j between 1 and k over 2, we can issue the following k query to the comparison oracle. In the query, we first set the first k by 2 elements to be points x prime and the next j elements to be x max. Such a k query can be shown to be equivalent to asking the human expert whether k by 2 times the gain for x prime is bigger or j times the gain for x max. Combining this with a binary search and varying the values of j appropriately, one can actually obtain a 2 by k approximate estimate of the utility gain of x prime. Similarly, by iterating over all the data points, one can obtain the estimates over the entire dataset. And with this, we complete the procedure for obtaining these estimates. So just to recap, our main algorithm is a two-step plug-in estimator in which the first step comprises estimating utilities u hat on the sample data points by interacting with the key comparison oracle. In the next step, the algorithm outputs the empirical utility maximizer with respect to these estimated utilities. Given this algorithm, the natural question to ask is what about the excess risk of this estimator, which was our original objective to begin with. Our main upper bound theorem precisely answers this question. In particular, it says that the plug-in estimator makes order n log k queries to the k comparison oracle and that its excess risk is upper bounded by a sum of two terms. The first term, which is a complexity term, captures the expressiveness of the function class f. This depends on how the utility u star interacts with the class f, but more importantly, it places no restrictions whatsoever on this utility function u star. More formally, this term captures the rate of uniform convergence of the class f when evaluated on the utility u star. The second term is a product of two terms. The first is a factor of the order of 1 over k, and the next one is the misprediction error of the optimal ERM function. Observe that in the well-specified case, when the ERM correctly predicts the labels of each data point, this term vanishes and one does not pay any additional error for not knowing the utility function. Thus, the consequences of not knowing the utility function only come up in the misspecified setup. Further, note that this theorem provides an example of an interesting accuracy elicitation trade-off. As the order k of the comparison increases, the error decreases at a rate of 1 over k. However, as we had earlier noted, increasing this order also makes eliciting accurate responses from the human expert harder. Thus, by varying this value of k, one can cover an entire spectrum of this trade-off. It's also important to note here that our proposed algorithm is actually query efficient. It makes order n log k queries to the k comparison oracle. And actually, any statistically efficient algorithm needs to make at least n queries to the oracle to learn about the utilities on all the data points. Now, given this upper bound, it's a natural question to ask whether this additional error term comprising of 1 over k and the error of the ERM classifier is indeed necessary, or is it just a manifestation of our analysis? To answer this, we prove a lower bound theorem which shows that for any k greater than 1, there exist prediction problems such that the minimax risk of any algorithm is lower bounded by a constant over k. Thus, we establish that our plug-in estimator is actually statistically minimax optimal. To conclude, our work formalizes a class of supervised learning problems wherein the underlying utility function is unknown to the learner a priori. We study a natural plug-in estimator and establish that it is statistically minimax optimal. Furthermore, in the course of our analysis, we also reveal an interesting accuracy elicitation trade-off within this framework. Please check out our paper to learn more.